if you go to Google and search, you can find the formula for the centroid of trapezoidal. And the formula for area is this cross this divided by multiplied by height divided by 2, right? But look, those things are complicated. You don't want to memorize things that are not necessary, right? So what's my best bet right now to solve this problem? To break it down into a simple rectangle like that and simple triangle. And I already know where the centroid is and what the area formula is. It's just so easy, right? So instead of doing one, I'll break it down into two problems. Now, I want to replace this guy with the point load. So if I eliminate this, I should first step, find the area under this rectangle. And step 2, find the centroid. And step 3, put the unit load at the centroid that is equal to the area, the value of point load. So the area of this guy is 6 times 150. So at the center, the centroid is just at the center. I put the unit load, you see that? And its value is 150 times 6. And the location is half of this distance, which is 3 from point A. Right? Now let's go to this triangle. The centroid is 1/3 of the height. What's the height? 6. 1/3 of 6, 2. So from here to here, from the base, is 2, and you put a unit load. You see? So, let's use the blue color. From here to here is 2. It's 1/3 of 6, right? So what's the value of the point load? The area under triangle. So what is height?
50.
50 times
2, right? Base times height.
Yeah, 50 times
3, 2.
yes, 6 divided by 2, which is 3. 50 times 6 divided by 2, right? Is the value of force. And the location is 2 feet from here. You see that? Now, as you can see, I can get rid of, I can cross it, or you can erase it, right? Or if you practice a lot, you don't even need to do that, because you know that there is no distributed load anymore. So you don't count it twice. Don't do that, right? All right, so right now let's do resultant force X. So find the resultant force in the X direction. So what's the resultant force in the X? 0. Nothing in the X, right? Resultant force in the Y direction. Let's start with this. So negative 500. So don't forget, your positive X is always to the right, unless I say, positive X taken to the left, which I don't. But sometimes you do. Later on, you may take positive X to the right, and then your positive Y become to bottom, and the Z is stuck here. So it doesn't really matter. If you see the coordinate system, you can decide which one is positive, which one is negative. In CAD software, you can see that 3-coordinate system at the corner of the screen. So when you rotate the model, you can see the coordinate system will rotate. You can move it. You can put it at different points, change it in CAD software. But the mechanism is exactly the same. So if this is positive, this is negative 500. This one, negative 3 times 50, and then negative 150 times 6. So that's my resultant force. X component 0, Y component is something negative. Put it in the calculator and get it, right? Now resultant moment at O. So with this, 500 times 3. Positive or negative? Positive. Go to the next one. 3 times 50 times. So this is 3 times 50 times the distance from here to here. So up to here is 6 plus 2, 8, right? Positive or negative? Positive. So you put the sign positive here. Now you go to the next one, this one. So 150 times 6 times distance. What's the distance? 9. Thank you. Positive or negative? That's it. So, if you put this in the calculator, let's put it in the calculator.
It's 10,800.
This one is
Oh, that one's 1,550.
1,550 negative, right? And this one?
Is 10,800.
10,800. Like that. Right? 10.8 K Newton. Right? So, if assuming that the computation is right, should I double check it or that's right? That's right? Okay. Alright, so at the end you can get rid of all these things and replace just one y component of force and one counterclockwise moment. So you have mr, which is equal to 10.8 K Newton meter, kilo Newton meter, times meter. And actually pound, that's pound, pound foot, right? And this is pound, FBD. So kilo foot, and then you have 1,550 down. So then you can get rid of everything else. You simplify it. That's it. This system is equal to all of this unit load plus 1 point load here. They're exactly equal. They're mathematically equal. Right? Now, let's go to another section. Non-uniform, or let's call it arbitrary distributed load. So let's say you have a complicated distributed load. So far we said you either get a uniform or rectangular or box distributed form or triangle, right? Now let's say you have a very complicated profile. Let's say you have something like this, right? As you can see, this variation is not linear and is not uniform. So what should I do? Let's say this is sort of point A and end as point B. And the value of curve is represented by omega, which is a function of x. So if you put your coordinate system here, if this is x, this is the value of load, omega x. So at each x from here, starting from here, at each x, location x, the height of this guy is omega at x. Let's say you have this system. Now, I want to find the value of force generated by distributed load. Let's call it resultant. I want to find resultant force, Fr, and resultant moment with respect to this point, Mr. With respect to, let's say this is point A, let's say O, 0, 0, origin, right? That's what I want to find. So in fact, I am trying to simplify, replace this at the center with just one force, one moment, the standard method of simplification. Now in the next step, I want to move that force sideways to get one single force that generates the moment implicitly. So at the end of the day, we have one force only with particular distance, right? At a very particular distance that is equal to all these distributed loads. So you no longer need a moment. So let's first find the value of force, resultant force. So in order to find the value of resultant force, I am going to consider a tiny band. So instead of this complicated profile, I just consider from here to here. You see this area. Let's say this is very, very thin. So what happens here is just very, very thin. What happens? Its width become dx. If this is x, then this width become dx. See that? dx. And its height is equal to omega at x, right? So what's the area under this tiny bar? The area is what? Area is equal to base times height. The base is dx, height omega x. So area is omega x dx. And this area is very small. So I say dA because it's infinitesimal, dA. Right? So this is the force generated by this band, this little area. Right? And consider this as a combination of point forces. Infinite number of point forces. So this is a kind of one point force. So what should I do in order to find the resultant? Add them up. And in the limit, because they are infinite, I do integral, right? So integral of all dA is A, or force, resultant force. Because each one of those, it was a single tiny force, right? Which is equal to integral omega x dx from where to where? From A to B, right? What about moment? What moment this little force generates with respect to 0, 0? Let's say this is df, right? So this dA is in fact also df. Let's say I have the df, right? So what moment this tiny force generates with respect to 0?
Yeah, times the distance.
Yeah, x times. So x times df is equal to the moment it generates with respect to 0. So infinitesimal moment. But what is df? Just let's plug the value. What's the df? X times, what was df? Omega dx. Omega x dx, right? I just plug df here. So this is infinitesimal moment. In order to find the resultant moment, what should I do? Take the integral of this. So resultant moment, m resultant is equal to integral x omega x dx from A to B, right? You see that? Now, at this point, I replace this guy with the resultant force, Fr, and resultant moment, Mr. Right? And I found the expression for, let me highlight this. This is Mr, expression for resultant moment, expression for resultant force. I found it, right? Using basic math. Now, this system, now I no longer have a distributed load. I have these two, one force, one moment. Now I want to move this sideways such that I generate the effect of moment, so I can go further and drop the moment and only have one force at a particular distance. So let's do that. Let's move this force at a particular distance like here. At a particular distance like D, let's say move it at a particular distance. So this is F resultant, move it at D. such that it generates exactly the same moment. So I go ahead and drop this moment because this force moved sideways can generate a moment. So what should I write for that? If this force at this distance is generated MR, can generate MR. What?
A moment divided by the force.
Yeah, so this force times distance, Fr times d is equal to resultant moment that we had before, Mr. Right? So d is equal to Mr over Fr. So what's Mr?
X, omega x, yeah.
Integral x omega x dx from a to b divided by Fr. Integral a to b omega x dx. There you go. These are the formula. If you go to page, let me bring a page number. If you go to page 143 and 144, these are the formula right there, and I wanted to show you how you find this formula. But look, we are not going to evaluate integrals because I know some students, they didn't have calculus or have the same time, right, in the same time. So I don't want to add complexity, but I just want you to know the machinery, how this thing works under the hood. So if you know it, later on when you have extra time, you can do integration. But this thing is going to be given as a formula to you, both the centroid and the area, right? Okay, so this is equation number 320, equation 320, page 144. Page 144. Now let's go to one example, example 3.21. Determine the value of the resultant force and its line of action, or what distance the resultant force will go through. So at the end of the day, you only have one force with a particular distance, not one force a moment. It's the second step of simplification. So the first step is to find resultant force. So resultant force is what? Integral omega x dx. From, let's say you put the center here, right? Put your xy here, right? So the integration is from 0 to 2. So let's plug in the value of omega x. 0 to 2, 60 x squared dx. Take 60 out, so you have 60. And that's cube over 3 from 0 to 2. So 60 divided by 3 is 20 times 2 to 3, 8, which is 160 newtons. So the amount of force that this distributed parabolic force generates, this profile, the total effect is 160 newtons. If I consider it a single load. Now, at what location that force acts? Now you use this formula. All right, the distance. So that d is equal to integral x omega x dx from 0 to 2 over integral omega x dx from 0 to 3. Right? Look, sometimes we need to reuse our information. We have already done this. It's right here. Don't do integration twice. You can, but I save the time. I say, well, this one is 160 already. You did it here. Right? So I just do the top divided by 160. So what's the top? The top is integral from 0 to 2. Right? X times, don't forget the x. X times omega x. Now omega x is 60 x squared and then dx divided by,
160.
thank you, 160. Right? So take out this 60, so 60 divided by 160, and then you have integral of x to the third power, and that's going to be x4 over 4 from 0 to 2. Right? So, which in fact, this gives you 2 to the 4. So 2 to the 4 is 16 divided by 4 times this, then you can say 200 divided by 160, 0 goes with 0, and then you simplify it with 8. This is going to give you 3, it's going to give you 2. So it's going to give you 3 over 2. So the distance from 0, the distance that the network or resultant force act is 3.2 meter or 1.5 meter. That's what we get. Now come back to the picture. See the figure? Now let's go to some engineering intuition. If I had a uniform load, what would be the D, the distance that force acts, the point force acts, if it was completely uniform? It's just the midpoint, so it would be 1, right? But look at this result. It's 1.5, right? It's 1.5. So that means your net force is somewhere here. It's shifted to the right. Why? Because we have more force here than here. It's not uniform anymore. Right? So it's interesting to check this, like sometimes if you have extra time and you're done, let's say I give you the question in the test or midterm or quiz or whatever, and you have extra time. Just come back and check, make sure that this makes sense. All right? If you D is 0, something is wrong. Right? Because you have some force here, it can never go through 0. Or if you get your D is more than 2, is like 3, out of the range. If something is wrong, it should be somewhere here. Right? The average of a bunch of things should be somewhere here. So you can figure it out. Now, I want to give you another example. Let's say in the test, I'll give you, let's write it here. I'll give you a very complicated profile. Like this. And the equation for that, omega x is r tangent r cosine square root of x6 minus 1 divided by e to the square root of x16 minus x4. Let's say I give this to you, and then this is omega, right? This is a distributed force. As you can see, this is very complicated. X omega. And also, I give you an answer. I don't say, like, give me the answer. I give you the answer. So this is the options. So let's say from here to here is 6, right? And the answers are A, 0, B, 3, C, 4.67, E, 6, and E is 6.67. So the question is find the location of resultant force. Resultant force, or D. D that we just computed. But the first thing you see is just complicated monster equation. And then you see something is wrong immediately, because I'm not supposed to take integrals, because this thing, you should use numerical methods to do this integration. You can't do it analytically by hand, right? So, what do you do? Is there anybody that knows the answer right now?
C.
C, right? Thank you, that's right. The answer is C. But trust me, there are a lot of students that don't know the answer. So the first thing you see when you give them the question in the exam, you see they immediately pull out the calculator and they try to work with the calculator. And this has, you can't do it. You may use a calculator to do this integration, but again, that's a long way and the result may not be accurate, right? So how do you solve this? Well,
Elimination.
huh?
Said elimination.
Yeah, but using some intuition. You don't need to go to the numbers. Just use some intuition. So let's say instead of this complicated thing, if I had a uniform distribution, where would be my D location that force acts on if it was purely uniform?
3.
3. But this guy is not uniform. So this answer is, you can reject this. Let me use it. We can reject 3 because this is not a uniform. It will never be at the exact center because it's not a uniform. So you go to the next possibility. It's not going to be at 0 because you have some load here, right? If you didn't have any force, it would be probably 0. But you can reject this. Now here comes to the 3 options. It will not be at 6, right?
The same reason would be.
If you had, for the same reason, if you had a point force at 6, yes, the line of action ended at 6. But it's not point force, this is distributed, so you can eliminate this. So to this guy, 1 is after 6, and 1 is before 6. This one, rejected, because it's after the range, it's not within the range. So the only thing that makes also sense is going to be somewhere here. You see? This location is 4.67, because this is the only answer that remains. Not because you computed, it's because the only answer that makes sense, right? So that's the way you can handle a lot of, in fact, in the real engineering world, a lot of things, you just get it by intuition. There is no way to compute it. You just get some estimation. Now, the only thing that makes sense is 4.67. And look, somebody else has done all this integration and get this result. But you can select it without doing it, because that's the only true answer that makes sense. Okay? Now let's go to the actual vector statics. Now, it's starting from chapter equilibrium, we now teach the actual vector statics that has application, and you enjoy doing it. Because you can what? You can solve systems and you can design, right? So it gives you wins. So far we have just done some bunch of mathematics and vector simplification and resultants and things like that, right? Without even knowing what would be the actual application in the real engineering world. Now I want to give you an example what we're going to do after chapter 4. In fact, after midterm, we're going to have actual problems. And the solution procedure is a little bit longer. So let's say one example. Let's say you have a pulley and there is a weight here. This weight here. How many chemical engineering students do we have? Chemical major? No chemical major? Okay. How many electrical majors? Okay, lots of electrical. Alright. So, here I'm going to give you an example. So we connect air to the system and system into the frame. And of course, the ratio here, K4, 5. And this is 10 kilogram. Let's say 10. Now let's do this. Let's do this. Because we have a lot of electrical engineers, positive 220 volt GND, and this is oscillator, and then so this is a solenoid, right? The solenoid is a coil that when you add voltage to it, this one is going to apply. There is another circuit here. It's going to actually cool it. Cool it. It's using the switches in electrical engineering. All the switch mechanism is based on this, right? So let's say this is big coil, so it applies a lot of force. So when you actually, there is a switch, let's say there is a on and off. There is a on, this is a switch, right? This is off, on, switch, right? When you put the switch, the voltage goes through this and this coil starts cooling this using magnetic force. That force, magnetic force, right? You will have a course called electromagnetics. And you will study how, depending on how much voltage you have and number of cores and the diameter of this, how much force you get. Let's say somebody gives you that equation. As a mechanical engineering student, you don't study that. Those people study electrical engineering. But let's say they give you the equation and you know how much force is going to apply this. So what happens when you add the switch is going to, this coil is going to pull this up, right? It's going to attract it, right? What do you say? It's going to pull it, right? And then what happens, this goes up. Like this side goes up. And this side, this is like a lifting mechanism. You see that? This goes down. And because this length is much bigger than this length, you get, with a small force, you get a lot of torque. And then this pulley is fixed to the ceiling, right? And then you can lift this weight, whatever this weight is. This weight by itself can be a system, right? So the mechanical system can be very complicated. Now what I want to say here is you can, after chapter 4, equation of equilibrium, you can analyze this. It's not just find the result of force. So far, the thing that we have done, they didn't really have any application. Like find the result of force, right? So what? But using the same thing we have done before, you should be able to analyze this. And if I ask you how much voltage you need, I'm not going to ask you, but maybe a final waiver or maybe a semester waiver. So if you do it, if you get the actual answer, you get your semester waived. Attention, electrical student engineering students. You will be able, practically, you will be able to find the value of voltage that you require to lift this 10K. If I give you all the parameters of this coil and all the, the connectivity and everything, the distance, everything. The actual value, like we say, like 280 volt, 0.4 volts I need in order to lift this 10K using this mechanism. Now, how do we do that? Right now, we have no idea. You see, we have no idea how to do that. But I am going to take you step by step to a procedure. It's a 5-step procedure. That if you 5 steps procedure, that if you do it systematically, you should be able to analyze the entire system, including the force in this cable. You can find the force in the cable. You can find the reactions. This is mechanical, civil engineering problem. Now you can also find the force required to lift this up. And if you know that force, you can find the configuration of this coil if you are an electrical major. We're not going to do it in the course, but I may give you the equation in one particular occasion and say, just do the machinery and find the unknowns. All right? So basically, you can do anything. So that's the reason I said this course for mechanical and civil engineering students is the most fundamental course, because everything is the fundamental course in your entire 30 years of career working. Right? So let's start this procedure. This procedure, in fact, is select system. Now I'm going to talk about system soon. 2, draw FBD free body diagram. Let's write it here. Free body diagram. Right? This goes to VCC, and also this is level G. Because if you don't have current in this, it's not going to pull it. You have to have current in both of them. So draw FBD step 3. Write equation of. You have no idea right now about all these things, but we are going to go a step into every single one of these, right, soon. So I just want to give you the overview. Write equations of equilibrium. For solve. You see these equations, because you may end up with a lot of equations. Soon we will see. We start with just simple 3 equations and then we go up. We may have multiple systems, so you do everything for per system. This is per system. Solve the equations. So you have a step for solve. Don't write the equation and solve it right away. That's going to mess up your concentration. Just write all the equation and then come back and solve it. 5, verify the results. If you can. You cannot always verify, if you can. For example, if I solve this particular problem and I get tension in the cable is negative, that means compression. then you can say something is wrong, right? If you get a negative number. So you may go back and iterate. Probably you have chosen the wrong system or wrong FBD, or there is something some sign wrong in the equations, or you have done the solution procedures wrong. Something is wrong. Now next class I want to talk, next class we have tests, right? After that I want to talk about system and FBD. Right? And then we have another class on equation and solve, and then we're going to have lots of more class for example, problem solving. All right? Okay.